Every atom in your body is almost entirely empty space. Your hand, your bones, your brain, 99% empty, down to the deepest level we can measure. Scientists assumed that emptiness was simply nothing. They were wrong. Empty space seethes. It churns, it builds mass, pulls metal plates together, changes how electrons behave inside materials, and may be driving the expansion of the entire universe. And in February 2026, for the first time in history, scientists watched real particles emerge directly from the void. We will go inside a proton, stand at the edge of a particle collider, and follow the discovery that rewrote what space even means. If you enjoy the journey, like and subscribe. It genuinely helps. Now, let us begin. For most of human history, empty space meant one thing: nothing. Pull out all the air, block every beam of light, remove every atom. What remains is a blank, a void, a total absence. That idea felt clean, it felt logical, and for centuries the greatest minds in science built their entire picture of the universe on top of it. Isaac Newton used it. He described space as a fixed passive container. Matter moved through it. Forces acted across it. But space itself did nothing. It was a stage, and the universe performed on top of it, without the stage ever getting involved. James Clerk Maxwell, who figured out the laws of electricity and magnetism in the 1800s, tried to fill the void. He believed empty space had to contain something, a hidden medium he called the ether, that carried light waves the way water carries ocean waves. That idea collapsed in 1887 when two scientists built a machine to detect the ether and found absolutely nothing. Space seemed emptier than ever. Then Albert Einstein arrived. He bent space. He curved it. He showed that gravity warps the geometry of space and time together. Space was no longer just a container. It was a flexible structure that could stretch and twist around massive objects. The universe got stranger, but space itself still had no energy of its own. It was still, in Einstein's framework, fundamentally passive. That picture held for roughly the first half of the 20th century. Physicists had enough to work with. Atomic theory, relativity, and the early ideas of quantum mechanics kept everyone busy for decades. The void stayed quiet. Then quantum mechanics matured, and it handed everyone a problem nobody had asked for. The Heisenberg uncertainty principle, developed by Werner Heisenberg in the 1920s, set a hard limit on how precisely you can know two related properties at the same time: position and momentum, energy and time. The more precisely you pin down one, the less precisely the other can be known. This is not a flaw in your measuring tools. It is baked into the structure of reality at the deepest level we can probe. Here is where the void breaks down. If a region of space had exactly zero energy, that would mean you knew its energy with perfect precision. Zero, always, forever. But the uncertainty principle says you cannot know both the energy of a region and the timing of that energy state with perfect precision simultaneously. A perfectly zero energy region, frozen and locked at zero for all time, would violate the uncertainty principle. The universe does not allow it. So space can never be fully empty. The lowest energy state anything can reach still contains fluctuations, still contains something. That floor of minimum activity, the lowest level every quantum field can settle to without violating the laws of physics, is what scientists call the quantum vacuum. The quantum vacuum is everywhere. It fills every cubic inch of space in the entire universe, including the space inside your body right now. And it never stops moving. For a long time, physicists knew it was there, but treated it mostly as a mathematical nuisance, a background hum they had to account for in their equations, something small, technical, and easy to set aside. They were wrong about that too. The first sign that the quantum vacuum was doing something real and physical came from the simplest possible experiment you can imagine: two metal plates, a vacuum, and a force that had no right to exist. Werner Heisenberg was 24 years old when he had the idea that would make true emptiness impossible. It was 1925. Heisenberg was working in Göttingen, Germany, trying to fix a problem at the heart of early quantum mechanics. The math kept producing infinities where it should have produced clean answers. One night, building a new mathematical framework almost from scratch, he stumbled onto something that went far beyond fixing equations. He found a fundamental limit, a hard ceiling built into reality. The uncertainty principle states this. Certain pairs of properties are linked in a way that means knowing one precisely makes the other blurry. The two most famous are position and momentum. The more exactly you locate a particle, the less you can know about how fast it is moving. The other critical pair is energy and time. The more precisely you want to know a region's energy at a specific moment, the less precisely you can specify when that measurement applies. This sounds like a quirk of measurement, like maybe your ruler is just too crude, but it runs deeper than that. The uncertainty principle is a statement about nature itself. A particle does not have a perfectly defined position and momentum at the same time. The blurriness is not in your instruments. It lives in the particle. Quantum objects exist in smeared-out states. Pinning one property down physically forces the other to spread. Carry that into empty space. A region of perfectly empty space would, by the classical definition, have exactly zero energy. Zero. Absolute. Constant. Every measurement at every moment would return the same answer. That means you know the energy with perfect precision, and you know it holds that precise value across all time. Both energy and time pinned down simultaneously. The uncertainty principle says that cannot happen. The universe physically prevents it. So space cannot sit still at zero. Energy must fluctuate. It must wobble up and down around that minimum value, never locking in. The floor of the universe is alive with motion, and there is no level below it, no way to reach true stillness, no configuration where everything stops. That floor is called the zero-point energy. Every quantum field has one: the electromagnetic field, the field associated with light and photons, the fields associated with electrons and quarks, and every other particle. All of them permeate all of space. All of them fluctuate. All of them sit on their own zero-point energy floor, jittering continuously at the minimum level physics allows. Picture a trampoline that can never be fully flat. Even with nothing on it, the fabric always has some bounce left. Press it down toward flat, and it pushes back. That is the quantum vacuum. The universe's trampoline that never settles. Now picture that trampoline covering every cubic inch of space, in all directions, forever. These fluctuations are not slow or gentle. At the tiny scales where quantum effects dominate, the fluctuations are wild, constant, and powerful. They produce brief spikes of energy, and those spikes have consequences. The first consequence involves particles. When the energy fluctuation in a quantum field spikes high enough, even briefly, it can produce a particle-antiparticle pair. They flash into existence together, borrowing energy from the fluctuation, and then almost instantly vanish as they annihilate each other. The whole event lasts a fraction of a second. These are called virtual particles. Virtual particles have effects on the real world, measurable, confirmed effects that change the direction of physics. And the story of how scientists first detected those effects involves two plain metal plates, a vacuum chamber, and a prediction so strange that most physicists assumed it would remain untestable forever. The name is misleading. Virtual particles sound like something invented for a science fiction story, a mathematical trick, a metaphor physicists use to make complicated equations easier to explain. They are real, their effects are measurable, and they are happening everywhere, including in the space between your hands right now. Here is what a virtual particle actually is. The quantum vacuum fluctuates constantly. Energy spikes up and back down in tiny, rapid bursts. When a spike is large enough and brief enough, quantum field theory says something specific happens. A particle and its antimatter partner appear together, borrow that spike of energy from the vacuum, and then annihilate back into each other almost immediately, returning the energy they borrowed. The key word is borrowed. The Heisenberg uncertainty principle allows this. Because energy and time are linked, a large fluctuation in energy is permitted as long as it lasts for a very short time. The bigger the energy spike, the shorter it must last. A pair of very heavy particles can appear, but only for an almost unimaginably brief instant. Lighter particles can stick around fractionally longer, but even then the timescales are so short that no detector on Earth can directly catch the pair in the act. This borrowing is sometimes called a quantum loan. The universe allows you to take from the vacuum, but it collects immediately. No particle born this way can persist. The debt always gets paid. So why do they matter? Because while they exist, virtual particles interact with real matter. They push on things. They pull on things. They alter energy levels. The effects are tiny in most situations, but they add up, and under the right conditions they become large enough to measure with precision instruments. Think of the vacuum as an ocean. Virtual particles are like waves. You cannot hold a wave in your hand, but waves still move ships, carve coastlines, and carry enormous energy. The vacuum's waves cannot be grabbed or stored, but they press against every surface, every particle, every atom in the universe, all the time. The kinds of virtual particles that appear depend on the quantum fields involved. The electromagnetic field produces virtual photons, the particles of light. The strong nuclear force field produces virtual quarks and gluons. Each field has its own flavor of vacuum fluctuation, and each leaves its own fingerprints on the physical world. Those fingerprints show up in specific ways. Virtual photons produce tiny shifts in atomic energy levels. Virtual quark-antiquark pairs contribute to the mass of protons and neutrons. Virtual particles between two surfaces create a measurable force. Each of these effects was once considered theoretical, a prediction waiting to be checked. One by one, they were confirmed. The confirmed status of virtual particle effects is what makes the quantum vacuum a scientific fact rather than a philosophical idea. Physicists are not guessing that the vacuum fluctuates. They have measured the consequences multiple times in multiple independent experiments using completely different methods. The fingerprints are there, and each fingerprint pointed somewhere new. The first one pointed at two metal plates and a force that should not have existed in classical physics. A Dutch physicist worked it out on paper in 1948. He gave the force a name. For nearly 50 years, almost no one could build a machine sensitive enough to confirm it. Then someone did, and the vacuum was never just background noise again. Place two flat metal plates inside a vacuum. Keep them parallel. Space them about 4 millionths of an inch apart. Do not charge them. Do not connect them. Do anything. Do not touch them. They will move toward each other. No magnets, no static electricity, no current, no physical contact. The plates sit in what looks like perfect emptiness, and yet something pulls them together. This is the Casimir effect, and it is one of the most direct demonstrations that the quantum vacuum is physically real. To understand why the plates move, picture the vacuum filling all of space with virtual photons, the quantum fluctuations of the electromagnetic field. These virtual photons come in every possible size: short wavelengths, long wavelengths, medium wavelengths, the full spectrum, in all directions, everywhere. Now put the two plates in. Between them the space is tight. Only virtual photons whose wavelength fits into that gap can exist there. A wavelength longer than the gap cannot squeeze in. Think of it like trying to fit a school bus inside a parking space made for a compact car. The bus simply does not fit. Outside the plates, the vacuum fills with every wavelength freely, the full crowd. Inside the gap, only the small ones get through. That means the energy density of the vacuum between the plates is slightly lower than the energy density outside the plates. An imbalance forms. The outside pushes harder than the inside. The plates get shoved together. The force is tiny. For plates about 4 millionths of an inch apart, Casimir calculated it at less than 1/1000th of a newton. 1/1000th of a newton is roughly the weight of a single red blood cell. For most of the 20th century, no instrument existed that could detect something that small reliably. For 50 years, the Casimir effect sat in the physics literature as a fascinating prediction with no experimental proof. Then the gap between the plates grows even smaller. As you bring two surfaces within about 4/10,000ths of an inch of each other, 1 micrometer in metric terms, something changes. The Casimir force becomes the strongest force acting between them, stronger than gravity, stronger than any residual electrical effect. In that regime, the vacuum is the dominant actor. This matters enormously for engineering. Microscale machines, devices with moving parts, measured in millionths of an inch, operate in exactly that regime. At those scales, the Casimir force can cause tiny components to stick together permanently. Engineers designing devices at that scale have to account for it the same way a bridge engineer accounts for wind load. The vacuum is not academic at these sizes. It is a practical force with practical consequences. There is one more twist to the Casimir story that most people never hear. In 1956, a physicist named Yevgeny Lifshitz showed that for certain types of materials, the Casimir force can reverse. For specific combinations of materials, the vacuum pushes plates apart rather than together. Repulsive Casimir force. Researchers have since used this effect to study frictionless levitation at the nanoscale. The same quantum vacuum that pulls things together can also push them apart, the same empty space. For decades, this stayed a laboratory curiosity. Then someone built a machine sensitive enough to actually measure it, and the result changed what physicists thought the quantum vacuum was capable of. Hendrik Casimir was 38 years old in 1948 and working at the Philips Research Laboratories in the Netherlands. He was a careful, methodical physicist, well respected but not yet famous. That year he published a short paper, less than 3 pages long, that most of his colleagues read once, filed away, and largely forgot. The paper predicted that 2 uncharged metal plates in a vacuum would attract each other through a force generated entirely by the quantum vacuum. The force had no classical explanation. It came from the geometry of empty space. Casimir arrived at the idea through a conversation with Niels Bohr, one of the founders of quantum mechanics. Casimir had been working on a related problem involving forces between molecules and mentioned his calculations to Bohr during a walk. Bohr suggested the underlying cause was zero-point energy, the unavoidable minimum energy of the quantum vacuum. Casimir went back to his office, reworked the mathematics, and produced the prediction that now carries his name. The reaction from the physics community was not hostile. It was closer to polite indifference. The force Casimir predicted was absurdly small by everyday standards. Measuring it would require plates machined to extraordinary flatness, positioned with precision measured in millionths of an inch inside a vacuum, with all vibrations, static charges, and temperature effects controlled or eliminated. In 1948, that was beyond any available laboratory. The technology simply did not exist. So the prediction sat. 10 years later, in 1958, a physicist named Marcus Sparnay attempted the first measurement. He built a device, took readings, published results. His conclusion: the measurement was consistent with Casimir's prediction, but the experimental errors were so large that the result was effectively inconclusive. His honest summary was that the data did not contradict Casimir. That was the best anyone could say. The experiment sat dormant for nearly 4 more decades. Meanwhile, the quantum vacuum continued to accumulate theoretical importance. The Lamb shift, confirmed in 1947, already showed that vacuum fluctuations shifted atomic energy levels. Quantum electrodynamics, the most precisely tested theory in all of science, required the vacuum to behave exactly as Casimir described. Every calculation assumed the vacuum was real and active, but a direct measurement of the Casimir force remained elusive. Part of the difficulty was philosophical as well as technical. Many physicists were skeptical that a force born purely from the geometry of empty space was meaningful in the same way that a force from a battery or a magnet was meaningful. Some argued the Casimir force was just a long-range version of the molecular attraction that operates between surfaces anyway. The deeper question, whether the quantum vacuum itself was generating the force, remained open. Casimir himself continued working in physics and industrial research for decades. He lived to see his prediction confirmed. He died in 2000 at the age of 90, just 3 years after the measurement he had waited 50 years for was finally made. That measurement, when it came, was clean, precise, and it left no room for the skeptics. The physicist who made it built his apparatus in a university basement. He spent months controlling for every source of error he could imagine, and when he finally ran the experiment, the result matched Casimir's 50-year-old equation to within 5%. The quantum vacuum had passed its first real experimental test, but the deeper implications of that force, what it meant for matter at the smallest scales, had barely begun to surface. Stephen Lamoureux had a reputation for extreme care. He was not flashy. He was not chasing headlines. He was a physicist at the University of Washington who decided in the early 1990s to do something almost nobody else thought worth attempting: build a machine sensitive enough to measure the Casimir force directly. The challenge was staggering. The force Casimir predicted between surfaces separated by about 4 millionths of an inch amounted to less than 1 billionth of a Newton. To give that number a physical picture, it is roughly the weight of a single human cell. Detecting it required eliminating every other tiny force that might interfere: vibrations from traffic outside, static charge on surfaces, temperature differences between the plates, even the faintest magnetic fields. Lamoureux did not use 2 flat plates. The precision required to keep 2 large flat surfaces perfectly parallel at millionths of an inch separations was beyond any available machining technology. Instead, he used a flat plate and a small gold-coated sphere. A sphere always presents a consistent curved surface regardless of exact orientation, which made the geometry controllable. He mounted the sphere on a torsion pendulum, a device that twists slightly when a force acts on it. The amount of twist tells you the size of the force. He placed the flat plate close to the sphere, measured the twist, and compared the result to Casimir's equation. He spent months checking the apparatus. He accounted for electrical patch effects, tiny voltage differences across metal surfaces. He controlled temperature to fractions of a degree. He isolated the device from building vibrations. Every possible source of error got its own correction factor, measured and documented. When he ran the experiment and published the results in 1997, the measured force matched Casimir's 50-year-old prediction to within 5%. For a measurement this delicate, at forces this small, 5% was extraordinary. Physicists called it a triumph of experimental precision. The Casimir effect was real. The force from nothing was real. The quantum vacuum was pushing physical objects in a measurable, predictable way. The physics community's response was immediate. Other groups replicated the measurement. Newer experiments reduced the uncertainty further. By the early 2000s, the Casimir force had been confirmed across a range of separations and geometries to accuracies better than 1% in some configurations. It is now listed among the best confirmed predictions in all of quantum physics. But what made Lamoureux's result more than a curiosity was where it pointed. Engineers working on microscale machines, the tiny devices being built into sensors, medical tools, and electronic components, had started running into a strange problem. Components at the microscale would stick together unexpectedly. Surfaces that were supposed to move freely would fuse. For years, the cause was unclear. After 1997, the answer was obvious. The Casimir force negligible at human scales, becomes the dominant force between neutral surfaces below a certain tiny distance. The vacuum was physically interfering with devices. Lamoureux had not just confirmed a theoretical prediction, he had identified a force that engineers now had to design around. Something stranger still waited in the Casimir story. The same vacuum fluctuations that pull surfaces together could, under the right conditions, do the opposite. And that reversal turned out to have its own set of surprising uses. The Casimir effect pulls. Two surfaces in a vacuum get pushed together by the pressure of quantum fluctuations. That part is confirmed, measured, and now engineered around. But in 1956, a physicist named Yevgeny Lifshitz worked out the full theory of forces between real materials in a vacuum, and he found something Casimir's original calculation had missed. For certain combinations of materials, the Casimir force reverses. The vacuum pushes surfaces apart. This sounds like it should be impossible. The whole mechanism behind the Casimir attraction is the pressure imbalance between the restricted vacuum inside the gap and the unrestricted vacuum outside. How does reversing the force even work? The answer lies in how different materials interact with the electromagnetic field of the vacuum. Virtual photons, the electromagnetic fluctuations of the vacuum, do not interact with all materials the same way. When a virtual photon hits a metal surface, it gets reflected. When it hits a dielectric material, a class of materials that includes things like glass or certain liquids, it gets partially absorbed and partially transmitted. The exact response depends on the material's electrical properties at different frequencies of light. Lifshitz showed mathematically that if you place two surfaces in a liquid medium rather than in a pure vacuum, and if you choose the right combination of solid materials and liquid, the vacuum fluctuations can produce a net outward pressure instead of an inward one. The energy balance flips, the force pushes rather than pulls. This repulsive Casimir force was measured experimentally for the first time in 2009 by a team at Harvard. They placed a gold surface and a silica surface in a liquid called bromobenzene. The vacuum fluctuations of the electromagnetic field, modified by the liquid medium, produced a measurable repulsive force between the two surfaces. The measurement matched Lifshitz's theoretical predictions. The implications for engineering were immediate. A repulsive Casimir force means surfaces can, in principle, be made to float above each other without physical contact, without magnets, without any external energy input, just the quantum vacuum holding them apart. Researchers at several laboratories have since explored this for frictionless bearings, surfaces that slide against each other without ever actually touching, at scales too small for conventional lubricants to work. At the nanoscale, this matters enormously. Machines with parts measured in millionths of an inch face a constant problem. Surfaces stick. Friction at that scale is catastrophic. A surface that floats on vacuum repulsion never sticks. It never wears. It operates on the permanent activity of empty space. The engineering applications are still mostly theoretical or early stage, but the physics is confirmed. The quantum vacuum can be repulsive or attractive, depending on what you build around it. And this is where something deeper starts to emerge in the story of the quantum vacuum. The Casimir effect showed that empty space pushes and pulls on surfaces. But surfaces are made of atoms. Atoms contain electrons. If the vacuum exerts forces on surfaces, what is it doing to the electrons inside individual atoms? That question had already been answered, quietly and precisely, 50 years earlier. The answer came from a hydrogen atom, the simplest atom in existence. And what it revealed about the vacuum shook the foundations of quantum theory. In 1947, quantum mechanics had a problem. A tiny one. So tiny that most physicists might have ignored it. But one physicist did not, and what he found changed everything. The best quantum theory of the time, developed in the 1920s and 1930s, made extremely precise predictions about hydrogen, the simplest atom. one hydrogen nucleus, one electron orbiting it. The theory predicted specific energy levels, the exact amounts of energy the electron could hold as it sat in different orbits around the nucleus. These predictions were extraordinarily accurate, better than almost anything else in science. There were two specific energy levels the theory said should be identical, two different arrangements of the electron that should hold the exact same amount of energy. Identical, the equations said. The same. Willis Lamb measured them in 1947. They were different. The gap was small, enormously small. But it was real. The two energy levels that theory said should match were offset by a precise, measurable amount. That offset is now called the Lamb shift. Lamb won the Nobel Prize in Physics for finding it in 1955. The question the shift raised was immediate and urgent. If the best quantum theory of the time predicted those levels were identical, and they were not identical, then something was missing from the theory. Something was acting on the electron, nudging it, shifting its energy, and the equations had no term for it. The answer was the quantum vacuum. Quantum electrodynamics, the upgraded version of quantum theory that accounts for how light and matter interact at the quantum level, showed exactly what was happening. The electron in a hydrogen atom does not sit still in its orbit. The vacuum's electromagnetic fluctuations constantly bombard it, pushing it slightly away from the position it would occupy if space were truly empty. That tiny wobble shifts the energy levels. The two levels that should be identical end up slightly different because the vacuum treats them differently. The vacuum was actively perturbing the simplest atom in existence, and it was doing so with enough precision that the shift could be calculated to extraordinary accuracy and confirmed by experiment. The Lamb shift is now one of the most precisely verified predictions in all of science. Theory and experiment agreed to better than 1 part in 10 million. This was a turning point. The Lamb shift proved that the quantum vacuum does more than generate forces between surfaces. It reaches inside atoms. It changes the fundamental properties of matter. It rewrites the energy structure of the building blocks of everything. And quantum electrodynamics, the theory built to explain the Lamb shift, did more than solve one puzzle. It became the template for the entire standard model of particle physics, the framework that describes all known forces and particles. Every prediction that framework makes rests on the same foundation, a quantum vacuum that never rests, that acts on matter constantly, and that cannot be switched off. The hydrogen atom had been the simplest system physicists could study. If the vacuum was altering hydrogen at that level of precision, what was it doing to more complex systems? To protons which contain quarks? To engineered quantum devices? The answers came decades later, and they were far more extreme than anyone expected. Willis Lamb was methodical, skeptical, and relentlessly precise. In the mid-1940s, he was working at Columbia University with his graduate student Robert Rutherford, trying to build an experiment that had never been attempted before. He wanted to measure the energy levels of hydrogen more accurately than anyone had managed using previous spectroscopic techniques, which relied on analyzing light. Lamb and Rutherford took a different approach. They used microwave radiation instead. The technique involved producing a beam of hydrogen atoms in a specific excited state, bombarding that beam with microwave signals of varying frequencies, and watching for the precise frequency that caused transitions between the two energy levels in question. If the levels were identical, as theory predicted, no microwave frequency would drive the transition cleanly. If the levels were different, a specific frequency would resonate with the gap, like a tuning fork resonating with a musical note. The setup required control over every variable. The hydrogen beam had to be pure. The microwave source had to be tunable with precision. The detector had to catch the shift in atomic states reliably. Lamb and Rutherford spent months building and calibrating the apparatus. When they ran the measurement, the resonance appeared, a specific microwave frequency corresponding to 1057 MHz drove the transition cleanly. The two energy levels were offset by exactly that amount. The gap was real. Lamb announced the result at a conference in June 1947, before the full paper was published. Physicists in the audience immediately recognized the significance. Hans Bethe, one of the most brilliant theorists of the era, reportedly calculated a rough theoretical explanation for the shift on a train ride home from the conference. His estimate matched Lamb's measurement closely. The calculation Bethe sketched, refined by others over the following years, required a completely new approach to quantum theory. The previous framework had treated the vacuum as inert. To explain the Lamb shift, theorists had to account for the vacuum's electromagnetic fluctuations interacting with the electron. This required the technique called renormalization, a method for handling the infinities that appear in quantum field theory calculations in a mathematically consistent way. Renormalization was controversial. Some physicists found it mathematically unsatisfying. Richard Feynman, one of its architects, famously described it as sweeping infinities under the rug. But it worked. The predictions it produced matched experiments with stunning precision, and it relied entirely on taking the quantum vacuum seriously. Lamb's result did something else. It showed that precision measurement was a tool for discovering new physics. By pushing the accuracy of hydrogen spectroscopy beyond what anyone thought necessary, Lamb found a crack in the existing theory. That crack led to an entirely new framework. That framework, quantum electrodynamics, then revealed that the vacuum's effects were everywhere, in atoms, in molecules, in machines. The Lamb shift in hydrogen was just the beginning of a much larger story about how empty space shapes the properties of everything inside it, including, it turned out, the quantum circuits that engineers now build from superconductors, where the vacuum performs the same trick it pulled in hydrogen, just in a very different arena. Willis Lamb found his shift in 1947. For 60 years it lived almost exclusively in atomic physics, a fact about hydrogen and the quantum vacuum that belonged to a rarefied world of single atoms and precision spectroscopy. Then, in 2008, a team of physicists found it somewhere nobody expected, inside a superconducting electronic circuit. Superconducting circuits are devices built from metals cooled to temperatures near absolute zero, where electrical resistance vanishes. At those temperatures, certain circuits behave like quantum objects. They do not follow the rules of classical electronics. They exist in quantum states. They are some of the most promising candidates for the physical hardware of quantum computers. The team connected one of these superconducting circuits, called a qubit, to a transmission line resonator, a precisely engineered channel that supports specific electromagnetic modes. The resonator had a vacuum state, a minimum energy configuration of its electromagnetic field, just like any quantum field. The qubit and the resonator were coupled together, and the qubit's quantum states were influenced by the vacuum fluctuations of the resonator's electromagnetic field. When the team measured the qubit's energy levels, they found a shift. The transition frequency of the qubit, the energy gap between its two quantum states, was slightly offset from what it would be in the absence of the resonator's vacuum field. The shift was up to 1.4% of the full transition frequency. For a quantum circuit, that is enormous. A 1.4% shift means the device behaves differently from its design specifications, and the cause is the vacuum fluctuations of the electromagnetic field it sits next to. This was a Lamb shift. Same physics, new setting, and a critical result for anyone trying to build quantum computers. Quantum computers rely on qubits maintaining precise known quantum states. If the vacuum is shifting those states, that shift has to be accounted for in the device design. The vacuum is not passive background noise in these systems. It is an active participant in how the device behaves. Engineers have to measure the vacuum-induced shift and either compensate for it or incorporate it into the circuit's operating parameters. The 2008 result made something concrete that had been abstract for 60 years. The Lamb shift was not just a historical curiosity about hydrogen, it was a real engineering constraint in the most advanced quantum devices being built today. The vacuum was sitting inside laboratory equipment, quietly nudging qubit states and demanding to be accounted for. This placed vacuum physics on a new footing. The quantum vacuum was no longer something that only mattered at particle accelerators or in highly specialized atomic physics experiments. It mattered at room temperature laboratories, inside devices you could hold in your hand if they were not cryogenically cooled. It mattered to people building the next generation of computing hardware, and if the vacuum altered quantum circuits, what else was it altering? The question pointed directly at the most fundamental building blocks of matter. If vacuum fluctuations could shift the energy levels of engineered devices, what was the vacuum doing inside the proton, inside the dense knot of quarks and gluons, at the heart of every atom in your body? The answer was one of the most staggering facts in all of modern physics. Pick up any object, feel its weight. The heaviness you feel comes from mass. Mass is what gravity pulls on. Mass is what makes things feel solid. Mass is one of the most basic physical properties of matter. Now ask where that mass comes from. The standard answer most people learn in school points to the Higgs boson, the particle discovered at the Large Hadron Collider in 2012. The Higgs field gives particles their mass. The heavier the interaction with the Higgs field, the heavier the particle. That answer is correct for some particles, and it is almost completely wrong for explaining where the mass of the everyday world comes from. Here is the problem. A proton contains 3 quarks. Quarks have mass. The Higgs field gives them that mass. But if you add up the masses of 3 quarks, you get roughly 1% of a proton's total mass. 1%. The other 99% is unaccounted for if you only look at the quarks themselves. Every proton in your body, every proton in every atom of every object around you, carries mass that cannot be traced to the particles inside it. The quarks are almost irrelevant to the proton's weight. So where does the 99% come from? The quantum vacuum of the strong nuclear force. The strong nuclear force is the force that holds quarks together inside protons and neutrons. Its quantum field theory is called quantum chronodynamics, which physicists shorten to QCD. QCD predicts that the space inside a proton is filled with vacuum fluctuations of the strong force field. These fluctuations constantly produce virtual quark-antiquark pairs and virtual gluons, the carrier particles of the strong force. These virtual objects interact with each other and with the real quarks in a constant, violent churn. The energy stored in that churning is what constitutes the proton's mass. Mass, in this picture, is not a fixed property of a thing. It is the energy cost of the vacuum activity happening inside that thing. Einstein's equation connecting energy and mass, one of the most famous relationships in science, shows that energy and mass are the same thing expressed differently. The vacuum energy inside the proton is the proton's mass. The quarks contribute almost nothing to the total. This means that virtually every kilogram you have ever lifted, every time you have stood on a scale, every car crash, every ocean wave, every mountain, everything with weight and substance in the physical world gets roughly 99% of its mass from quantum vacuum activity. The Higgs boson, for all its fame, is responsible for only a tiny fraction of the mass you can touch and feel. The vacuum built the world from the inside out. Understanding exactly how this happens, how the churning of the QCD vacuum produces such a precise and stable mass for the proton, is one of the most active areas of research in physics today. The theory called dynamical chiral symmetry breaking reproduces the proton mass in computer simulations. But the physical mechanism, the step-by-step story of how vacuum energy assembles itself into stable, measurable mass, is still an area of intense investigation. And the proton has another mystery. Its quarks account for only 35% of its total spin, a property as fundamental as mass. The rest of the proton's spin comes from the vacuum too. Scientists have been chasing the source of the missing spin for decades. The trail leads directly to the place on Earth where physicists can push the vacuum hardest. Quantum electrodynamics explains the Lamb shift. It explains light. It explains electricity. and magnetism at the quantum level. And it is extraordinarily precise. But the strong nuclear force, the force that holds quarks together and builds protons and neutrons, required something different, something wilder. Quantum chromodynamics, the theory of the strong force, was developed through the 1960s and 1970s. It describes quarks as carrying a property called color charge, a label with no connection to actual color, but used because there are three types of it, roughly analogous to the three primary colors of light. Quarks exchange color charge by firing gluons at each other. Gluons are the carrier particles of the strong force, the way photons are the carrier particles of the electromagnetic force. Here is where QCD becomes strange in a way that quantum electrodynamics is not. Gluons carry color charge themselves. Photons are neutral. They carry the electromagnetic force without being affected by it themselves. Gluons are different. Because they carry the very charge they transmit, gluons interact with each other. They can produce more gluons. They can form temporary loops and lots of energy. The strong force field does not just mediate interactions between quarks. It has a rich, turbulent internal life of its own. This self-interaction of the strong force field is what makes the QCD vacuum so extreme. In quantum electrodynamics, the vacuum contains virtual photons and virtual electron-positron pairs, but these fluctuations are relatively gentle. In QCD, the vacuum is a churning tangle of virtual quarks, virtual antiquarks, and virtual gluons, all interacting with each other constantly. The energy density of the QCD vacuum dwarfs the electromagnetic vacuum. The strong force vacuum fluctuations are orders of magnitude more violent. A property called confinement emerges from this. Quarks cannot exist alone. Try to pull a quark out of a proton, and the energy you pump in immediately creates a new quark-antiquark pair from the vacuum, which snaps back and keeps the quark bound. The vacuum seals quarks inside every time. You cannot have a free quark in nature because the QCD vacuum prevents it. The second major consequence is dynamical chiral symmetry breaking. This is the mechanism behind the proton's missing mass. In a world where the QCD vacuum were inactive, quarks would interact weakly at low energies, and the proton would be very light, close to the sum of three quark masses. But the constant condensation of quark-antiquark pairs in the vacuum, the way they pile up and fill the lowest energy state of the strong force field, generates a massive effective mass for the quarks themselves. This acquired effective mass propagates into the proton as a whole, building up the 99% that the Higgs field never provided. Proving this from first principles requires simulating the QCD vacuum on a computer, a technique called lattice QCD that breaks space and time into a grid of discrete points and calculates the vacuum fluctuations step by step. These calculations reproduce the proton mass with reasonable accuracy, but the physical story of how exactly the vacuum builds that mass, and where the missing spin goes, remains one of the deepest unsolved problems in the theory. That mystery drew physicists to the most powerful particle accelerator in the United States, and what they found there in early 2026 rewrote what science could say about the moment matter is born. In 1987, a collaboration of physicists in Geneva made a measurement they expected to confirm one of the most basic predictions of QCD. They measured the spin of the quarks inside a proton. Spin is a quantum property. Every particle has it. It is a form of internal angular momentum, like the rotational identity of the particle, and it comes in fixed amounts. A proton has a total spin of 1/2. 3 quarks, each contributing their individual spin, should add up to the proton's total spin. The simple quark model predicted the quarks carried the whole thing. The measurement came back with a different number. The quarks accounted for only about 35% of the proton's total spin. The remaining 65% had no clear source. Physicists called it the proton spin crisis. Where was the missing spin? The immediate candidates were the gluons, and the orbital motion of the quarks themselves as they circulate inside the proton. Later measurements showed that gluons carry a substantial fraction. Orbital motion contributes more, but the accounting remains incomplete decades after the original measurement. As of the most recent experiments, no single term fully closes the gap. The deeper question the crisis raised was this: if the simple model of a proton as 3 quarks failed so badly for spin, what else was it missing? The proton is not a neat packet of 3 particles. It is a bubble of quantum field activity. At any given moment, the vacuum inside the proton is producing and destroying virtual quark-antiquark pairs at enormous rates. These C-quarks, as physicists call them, participate in the proton's properties in ways the simple model never captured. The QCD vacuum does not merely surround the proton from the outside, it operates inside the proton constantly. The distinction between the proton's real quarks and the virtual quarks produced by the internal vacuum fluctuations is blurry at the quantum level. The proton is partly its 3 valence quarks and partly the seething vacuum activity trapped within it. This made the proton an even more compelling target for experiment. If the vacuum was building mass and contributing to spin, what else was it doing? And was it possible to create conditions extreme enough to watch the vacuum produce real particles from scratch, to catch the moment of birth directly? That required energy levels far beyond what any tabletop experiment could produce. It required a machine the size of a building, operating at the frontier of what engineering could achieve. A machine that accelerated protons to nearly the speed of light before smashing them together, specifically to agitate the quantum vacuum hard enough to reveal what lives inside it. That machine already existed, and the team running it had spent years designing an experiment to catch the vacuum in the act. On Long Island in New York, there is a federal physics laboratory that has been operating since 1947. The Brookhaven National Laboratory covers about 5,000 acres of land, employs thousands of scientists from around the world, and contains one of the most powerful particle accelerators on Earth. The machine is called the Relativistic Heavy Ion Collider, and it runs protons and heavy ions around a circular track about 2.5 miles in circumference. Inside the collider, particles travel in 2 beams that circle in opposite directions. They are accelerated by superconducting magnets, hundreds of them, spaced along the full loop. Each pass around the ring adds more energy. The beams accelerate faster and faster until the particles inside them are traveling at 99.996% of the speed of light. At that speed, something strange happens to time. Special relativity, the framework Einstein built to describe motion near the speed of light, predicts that a clock moving at that speed ticks more slowly from the perspective of a stationary observer. A proton traveling at 99.996% of the speed of light has an internal clock running at a tiny fraction of the rate of a clock in the laboratory. Time inside the proton, as measured from the laboratory, nearly stops. For the experiment, this matters because it flattens the proton. In its own frame, the proton is roughly spherical. Seen from the laboratory at that speed, the proton appears compressed, squashed into a pancake shape due to relativistic length contraction. When 2 such pancakes collide head-on, they slam into each other with a force that compresses the quantum vacuum into a region far smaller than a single proton. The collision energy available is measured in hundreds of billions of electron volts. That is enough energy to excite the quantum vacuum violently, enough to push virtual particle pairs across the threshold from flickering ghost states into real detectable particles. The collisions produce hundreds or thousands of new particles in a fraction of a second. The STAR detector, which stands for Solenoidal Tracker at RHIC, surrounds the collision point. It is roughly the size of a house, a cylinder about 40 feet long and 40 feet wide, packed with layers of sensors designed to track the paths of every particle produced in the collision. Each track is recorded electronically. The energy of each particle is measured. The direction of travel is logged. Computers process millions of events sorting through the data to identify specific particles and reconstruct what happened in the fractions of a second following each collision. The STAR detector had been used for dozens of major physics results before 2026, but the experiment announced that February was different. It was specifically designed to watch the quantum vacuum produce real matter and to trace those particles back to their origin in the void. To do that, the team needed particles with a very specific property. They needed particles whose spin state could be measured after production, particles that would carry a quantum fingerprint from the moment of their birth all the way to the detector. Lambda hyperons were the answer, and they were about to tell a story that had been waiting in the vacuum for 30 years. February 3rd, 2026. The STAR collaboration published their results in the journal Nature. The paper described what the team found when they sorted through millions of proton-proton collisions at the relativistic heavy ion collider, searching for a specific signal inside the wreckage. They were looking for pairs of particles, a lambda hyperon and its antimatter counterpart, an anti-lambda, both produced in the same collision, both traveling in nearly the same direction, and crucially, both carrying spin states that pointed the same way. That last part was the key. In a normal collision, particles are produced through a cascade of interactions. Energy gets converted into new particles through random, independent processes. The spin of any given particle comes out random. There is no reason for a lambda and an anti-lambda produced separately by a collision to share any particular spin relationship. They are independent products of a chaotic event. But the STAR team was looking for something different. They were looking for lambda-anti-lambda pairs that came from the same source, a virtual strange quark and a virtual strange antiquark that existed together as a pair inside the quantum vacuum before the collision. Virtual quark-antiquark pairs in the QCD vacuum form in a specific way. The two partners share the same spin orientation because they were created together, entangled from the start. If a collision could supply enough energy to push such a pair from virtual to real, both particles would carry that shared spin orientation as a signature of their origin. The STAR team found it. Across millions of events, lambda-anti-lambda pairs produced close together in angle showed a spin alignment of 18.1% above random. The two particles were pointing the same way more often than chance allowed. The statistical significance was 4.4 standard deviations. In particle physics, 5 standard deviations is the gold standard for a confirmed discovery. 4.4 is considered very strong evidence, especially for a first observation. The effect disappeared for pairs produced far apart in angle. This was exactly what the theory predicted. Pairs born from a single virtual quark-antiquark partner stay entangled only while they are close together. As the particles separate, the quantum connection breaks, and the spin correlation fades. The STAR data showed the correlation decaying with distance exactly as theory said it should. One of the study leaders described it this way: the particle pairs begin as quantum twins, born together from the vacuum carrying the same quantum identity, then separated by the energy of the collision into two distinct real detectable particles. This was the first time in history that physicists had directly traced real particles back to a virtual pair in the quantum vacuum, confirming both the origin of the particles and a theoretical prediction about the spin structure of the QCD vacuum that had been made 30 years earlier. The vacuum had been caught in the act, and the particles that carried the proof, the lambda hyperons, are among the most fleeting objects in all of physics. They existed for barely long enough to be real. A lambda hyperon is a composite particle. Like a proton, it contains 3 quarks. Unlike a proton, one of those quarks is a strange quark, a heavier variant that does not appear in ordinary protons or neutrons. Lambda hyperons do not exist in everyday matter. They have to be created in high-energy collisions, and they do not last. A lambda hyperon lives for about 1/10,000,000,000th of a second. To put that in physical terms, traveling close to the speed of light inside the STAR detector, A lambda hyperon travels roughly 1 inch before it falls apart. 1 inch? Then it decays into other particles, shedding energy and breaking into simpler components, as the strange quark converts into something lighter. That decay is exactly what the star experiment needed. When a lambda hyperon decays, the direction in which it falls apart is directly connected to the direction its spin was pointing. The decay products fly off in a pattern dictated by the quantum state of the parent particle. By measuring the direction of the decay products, physicists can work backward and reconstruct the spin of the lambda that produced them. The lambda itself is gone before any detector could touch it directly, but its fingerprint survives in the spray of particles it leaves behind. This is the quantum fingerprint that made the 2026 measurement possible. The star detector is designed to reconstruct exactly these kinds of decay chains. Its innermost layers track particles down to fractions of a millimeter, capturing the slight displacement between the collision point and the point where the lambda decayed 1 inch away. Software then matches the decay products back to the lambda, calculates the decay geometry, and extracts the spin direction. The team ran this reconstruction for every collision event that produced a lambda-anti-lambda pair. Then they compared the spin direction of the lambda to the spin direction of its antimatter twin, the anti-lambda, produced in the same collision. For pairs that came from a virtual quark-antiquark partner in the vacuum, both spins should point the same way. For pairs produced by random collision processes, the spins should show no preference. The strange quark was the critical choice. Strange quark-antiquark pairs are one of the most common virtual quark pairs produced in the QCD vacuum, predicted by theory to exist in large numbers inside the vacuum fluctuations of the strong force field. Using lambda hyperons, which contain strange quarks, gave the team direct access to the spin signature of these specific virtual pairs. The fact that the lambda lives for only 1 inch is almost a paradox. Its brevity is a problem for detection, but its decay products carry the spin information out of the collision region to the detector layers where they can be measured. The lambda is a messenger that dies delivering its message, leaving the message intact. Every inch of travel, every decay, every reconstructed spin direction in the star data was a vote in the same direction. By the time the team tallied all the votes, the answer was clear. The spin alignment was real. The quantum twins were real. The vacuum had produced them. The result confirmed something theorists had predicted, but never seen. And it rested on a deeper principle, one that connects the birth of these particles to one of the strangest concepts in all of quantum mechanics. Quantum entanglement sounds like magic. Two particles, linked somehow, sharing information about each other's quantum state, no matter how far apart they travel. Einstein called it spooky action at a distance, and spent years trying to prove it was wrong. He failed. Entanglement is real, confirmed in hundreds of experiments, and it was central to what the star collaboration measured in 2026. Here is what entanglement means in the context of the QCD vacuum. When the vacuum produces a virtual quark-antiquark pair, the two partners are entangled from birth. They share a quantum state. In a virtual strange quark-antiquark pair, theory predicts the two quarks must carry the same spin orientation, a consequence of how the strong force field creates them. They point the same way. They always have. That prediction was made theoretically in the mid-1990s, but could not be tested because virtual particles cannot be caught directly. The star experiment found a way around this limitation. When a collision provides enough energy to push the virtual pair into real existence, the entanglement does not vanish. The real lambda and anti-lambda that emerge from the pair carry the entanglement their precursors held. They start out as quantum twins, and for the brief moments while they are still close together, their shared spin state survives. As they separate and interact with the surrounding field, the entanglement degrades. The correlation weakens. Eventually, it disappears. This is exactly what the STAR team measured. Pairs produced close together in angle showed strong spin alignment. Pairs produced far apart showed no alignment. The transition between correlated and uncorrelated mapped precisely onto the expected distance scale for entanglement to survive in the collision environment. The data tracked the entanglement in real time across the collision debris. A theoretical prediction from 3 decades earlier said that virtual strange quark-antiquark pairs in the QCD vacuum carry parallel spins. The STAR result confirmed it with 4.4 standard deviations of statistical certainty. The prediction had been waiting for technology advanced enough to test it, and it survived the test intact. This result matters beyond the specific measurement. Every theory of the QCD vacuum makes predictions about the spin structure of virtual quark-antiquark pairs. Confirming one of those predictions directly validates the broader theoretical framework. It tells physicists that the tools they have been using to describe the vacuum, the equations, the lattice simulations, the field theories, are capturing something real about how the vacuum operates. That confidence strengthens every other prediction the theory makes, including predictions about how the vacuum builds mass, drives confinement, and shapes the structure of protons. The 2026 result also confirmed something profound about measurement itself. Physicists had always known that virtual particles were present in the vacuum. The Casimir effect confirmed their pressure. The Lamb shift confirmed their electromagnetic effects. But this was the first time scientists had traced the birth of real particles all the way back to a specific virtual pair, watching the quantum state of the vacuum parents survive into their real offspring. The vacuum had been not just detected, but read. Its internal quantum structure had left a legible mark on particles that a detector could catch, measure, and decode. What the STAR experiment found was the gentlest possible version of matter emerging from the vacuum. Energy from a collision provided the push. But physicists have predicted a far more violent way the vacuum can produce matter, one that requires no collision at all. Just a field, just enough force, and the vacuum breaks. I'll write chapters 18 through 33 now, continuing the escalating intensity and following all script rules. The headlines in February 2026 said, "Scientists had created matter from nothing." That is close to the truth, close enough to be exciting, but the full picture is stranger and more precise than any headline could hold. The vacuum is not nothing. That is the entire point of everything that came before. The vacuum is a state, the lowest energy state of every quantum field that exists. It seethes with fluctuations. It holds virtual particle pairs in a constant state of potential. It has structure. It has spin. It has energy. So when the STAR experiment pushed a virtual quark-antiquark pair across the threshold into real particles, it was not pulling matter from a blank void. It was promoting something that already existed in a ghostly borrowed form into something permanent, real, and detectable. The vacuum provided the raw material. The collision provided the energy to make it permanent. Think of it like ice and water. Ice is water in a different state. When you add heat, the water does not come from nowhere. It was always there, locked in a solid form. The energy unlocked it. What the STAR experiment did was similar. The vacuum held quarks in a virtual frozen state. The collision energy thawed them into reality. This distinction matters because it changes what the result tells us about the universe. The vacuum is not a blank. It is the most fundamental state of all matter and energy. Every particle that has ever existed came from a quantum field. Every quantum field has a vacuum state. The particles we call real are just excitations of those fields, raised above the vacuum floor by some source of energy. The virtual particles in the vacuum are the same fields, flickering below the floor, never quite reaching the threshold to become observable. The boundary between virtual and real is not a hard wall. It is a threshold. Cross it with enough energy and the virtual becomes real. Step back below it and the real returns to virtual. The STAR experiment crossed that threshold deliberately, using the energy of 2 protons colliding at near light speed to push strange quarks from one side to the other. What this tells us is that matter and the vacuum are not opposites. They are two faces of the same thing. Matter is the vacuum briefly excited above its minimum state. The vacuum is matter, temporarily at rest. The universe at its deepest level is one continuous field, and particles are just the moments when that field gets agitated enough to become visible. This view reframes some of the oldest questions in science. Where did the matter in the universe come from? The answer now involves the vacuum directly. The early universe was a state of extreme energy. That energy excited the vacuum fields above their minimum states. Particles appeared. Most of them annihilated with their antimatter partners and returned to the vacuum. A slight imbalance, still not fully explained, left behind the matter that forms every star, planet, and living thing. The story of the universe is the story of a vacuum that got disturbed, and the star results showed that disturbance can be recreated in a laboratory. Scientists can agitate the vacuum on demand, watch particles emerge, and trace their origin. That capability points toward a deeper question. If a particle collider can push virtual pairs across the threshold, what about a pure electric field? What if the field were strong enough? What happens to the vacuum when you stress it to its absolute limit? The answer was predicted in 1931, and it describes something so extreme that no machine on Earth has yet been able to test it directly. Forget the collision. Forget the proton beams. Imagine a different experiment. Take two electrodes. Apply a voltage between them. Make the electric field between the electrodes stronger and stronger, pumping in more and more energy until the field reaches an intensity that has never been achieved in any laboratory in history. At a specific threshold, something happens that has no classical explanation. The vacuum between the electrodes tears open. Electron-positron pairs rip out of the field and become real particles. Matter appears directly from what looks like empty space, with no collision, no beam, no incoming particles. Just a field strong enough to pull the vacuum apart. This is the Schwinger effect. Fritz Sauter first sketched the idea in 1931, recognizing that strong enough electric fields should destabilize the vacuum in a way that produces real pairs. Julian Schwinger formalized the full quantum electrodynamic calculation in 1951. The prediction is exact. The threshold field strength is approximately 1 million trillion volts per meter. At that intensity, the electric field has enough energy density to push a virtual electron-positron pair across the threshold from vacuum fluctuation into real, measurable particles. The number is extraordinary. 1 million trillion volts per meter is roughly 100 billion times stronger than the most powerful sustained electric fields any current laboratory can produce. The strongest laboratory fields created in brief laser pulses approach a fraction of 1% of that threshold. No experiment in free space has ever come close. So the Schwinger effect in pure vacuum has never been directly observed. It remains a confirmed theoretical prediction of quantum electrodynamics, one of the most precisely tested theories in science. But the direct free space version sits beyond any current or near-future technology. What makes the Schwinger effect conceptually important is what it says about the vacuum. The vacuum is stable only as long as the fields acting on it stay below the threshold. Push past it, and the vacuum becomes unstable. It cannot hold its virtual pairs in the borrowed ghostly state. They get ripped out. The ground state of quantum fields, the lowest energy state of the universe, can be destabilized by a sufficiently strong external field. This implies the vacuum has a breaking point, a limit where its structure fails. The vacuum is not infinitely resilient. Apply enough stress and it gives. The energy required to do this in free space is currently unreachable. But physicists found a shortcut. The same physics that governs electron-positron pair production in a strong electric field also governs electrons and holes moving through certain materials. And one material in particular behaves almost exactly like a miniature quantum vacuum. accessible in a laboratory with tabletop equipment. That material was discovered in a pencil factory in Manchester. It is 1 atom thick, and it became the most important vacuum simulator in modern experimental physics. The threshold field for the Schwinger effect in free space, 1 million trillion volts per meter, is not just a large number. It is a number that puts the original experiment in a category physicists sometimes call unreachable with current technology, possibly for decades or more. To understand why, consider what generating that field would require. The most powerful laser pulses ever produced concentrate enormous energy into an incredibly short burst, lasting femtoseconds, which are millionths of a billionth of a second. At peak intensity, the electric field inside the laser pulse approaches levels far beyond anything static equipment can achieve. These pulses represent the cutting edge of human ability to concentrate electromagnetic energy. Even these lasers fall short of the Schwinger threshold by a factor of roughly 100 billion. Closing that gap would require either lasers many orders of magnitude more powerful than any existing facility, or a fundamentally new approach to concentrating field energy. Several such approaches are being pursued. The European Extreme Light Infrastructure, a multinational research facility built across 3 sites in Eastern Europe, aims to produce laser pulses of unprecedented intensity by combining multiple beams into a single focused spot. A facility in China called the Station for Extreme Light has similar goals. Neither facility, as currently designed, is expected to reach the full Schwinger threshold. However, they are expected to enter a regime where nonlinear quantum vacuum effects become measurable for the first time. One such effect is vacuum birefringence. An extremely intense laser changes the optical properties of the vacuum itself. Light traveling through the region of the intense beam bends slightly differently depending on its polarization. This happens because the virtual pairs in the vacuum get partially polarized by the strong field, making the vacuum behave like a material with different properties along different axes. This effect has been observed in the magnetic fields around neutron stars, but never directly in a laboratory. Another effect within reach of near-future lasers is photon-photon scattering. In classical electrodynamics, 2 beams of light pass through each other without interacting. At extremely high intensities, quantum electrodynamics predicts they should scatter off each other through virtual electron loops in the vacuum, light deflecting light through the vacuum, with no material involved. A team at Oxford simulated this in full 3 dimensions in 2025, predicting the exact signatures that experiments should look for. The full Schwinger effect in free space may have to wait for technology that does not yet exist, but the core physics it embeds, the idea that the vacuum breaks under sufficient field stress, has already been tested, just not in free space. In a material that behaves like a scaled-down version of the quantum vacuum, researchers achieved it at field strengths billions of times smaller than the free space threshold. The physics was identical, only the scale changed, and the material that made it possible has already changed the direction of several different fields in physics. Graphene is a sheet of carbon atoms arranged in a honeycomb pattern, exactly 1 atom thick. It is nearly transparent. It conducts electricity with almost no resistance. It is 200 times stronger than steel by weight. It was isolated for the first time in 2004 at the University of Manchester by a team that stuck tape to a block of graphite and peeled off layers until a single atom sheet remained. It also behaves, under the right conditions, like a miniature quantum vacuum. Here is why. Electrons moving through graphene near a feature of its electronic structure, called the Dirac point, travel as if they have no mass. They behave as relativistic particles, moving at a fixed speed through the graphene lattice, the way photons move through vacuum at the speed of light. The mathematical equations that describe these massless electrons in graphene are nearly identical to the equations that describe electrons and positrons in the quantum vacuum of free space. This analogy runs deep. The Heisenberg uncertainty principle applies to these electrons. Virtual pairs of electrons and holes, the graphene equivalent of particle-antiparticle pairs, form and vanish constantly near the Dirac point. Apply an electric field to the graphene, and these virtual pairs can be pulled apart and converted into real, current-carrying electrons and holes. Exactly as a strong electric field in free space would pull electron-positron pairs from the vacuum. The critical field strength for graphene is billions of times weaker than the Schwinger threshold in free space. Laboratory equipment can reach it. In 2022, a team at the National Graphene Institute led by André Geim applied electric fields to a graphene superlattice device, a pattern of graphene etched into a precise geometric form that enhances the effect. They observed the analog of Schwinger pair production directly. Real electron-hole pairs appeared from the vacuum-like ground state of the material, driven by the applied field, with rates that matched the theoretical prediction. A year later, in 2023, a team in Paris made the measurement quantitative. They measured exactly how many pairs appeared per unit time at specific field strengths in doped graphene transistors, and the numbers matched the Schwinger formula with remarkable precision. These experiments confirmed the core physics of the Schwinger effect at accessible energy scales. The mechanism works. The vacuum, whether it is the vacuum of free space or the analogous ground state of a two-dimensional material, produces real pairs when stressed above a threshold. The gap between virtual and real can be crossed by a field alone. This made graphene one of the most powerful laboratory tools in fundamental physics. It allowed researchers to test ideas that would otherwise require particle accelerators or laser systems orders of magnitude more powerful than anything available. The strongest confirmation of the Schwinger mechanism came not from a billion-dollar facility, but from a flake of carbon thinner than a soap bubble. The graphene result raised an immediate question. If matter can emerge from a vacuum-like state in a material by applying a field, could the same technique be used to control how materials behave? Could the vacuum be used not just as a source of particles, but as a dial for adjusting the properties of matter? In 2025, a team of physicists from 3 continents answered yes, and they did it without any field at all. The largest physics laboratories on Earth are getting a competitor they never expected. Particle accelerators dominated fundamental physics for most of the 20th century. Now a different kind of machine is claiming space at the frontier. Ultra-intense laser facilities are being constructed across Europe, Asia, and North America, each designed to concentrate light into pulses so powerful that the vacuum itself begins to react. The European Extreme Light Infrastructure spans 3 countries. Its facility in Romania, called the Nuclear Physics Pillar, holds the world record for peak laser intensity as of 2025. Its facility in the Czech Republic focuses on attosecond physics, the study of processes that happen in billionths of a billionth of a second. The Hungarian site targets high-energy applications, including direct experiments on vacuum properties. Each of these facilities works by stretching a laser pulse out in time, amplifying it to enormous energy, then compressing it back into an extremely short burst. The peak power during that burst reaches levels measured in petawatts, which are 1,000 trillion watts. For comparison, the total electrical power consumed by the entire United States at any moment is roughly 1 trillion watts. These laser pulses, lasting a fraction of a trillionth of a second, carry 1,000 times that power concentrated into a spot smaller than a human hair. At those intensities, the electric field in the laser pulse approaches measurable fractions of the Schwinger threshold. The vacuum begins to respond. The first target is vacuum birefringence. When a region of space contains an ultra-intense field, the virtual electron-positron pairs in the vacuum get partially aligned by the field, making the vacuum behave like a crystal that slows light differently, depending on its direction. A second, low-intensity probe beam fired through the intense region would exit slightly changed, its polarization rotated by a tiny but measurable angle. Detecting that rotation would confirm that the vacuum has optical properties under extreme stress. The second target is photon-photon scattering. Two laser beams crossing at the right angle should produce a faint signal of scattered photons, light producing light through the vacuum, mediated entirely by virtual particles. Oxford physicists ran complete three-dimensional simulations of this process in 2025, predicting the exact signal shape and intensity that detectors should look for. The simulations showed the effect is within reach of the next generation of facilities. China's Station for Extreme Light, still under construction, targets 10 times the peak power of any existing facility. Its designers explicitly state that reaching the Schwinger threshold directly, producing real electron-positron pairs from a pure laser field in vacuum, is a long-term goal. If any of these facilities succeeds in observing vacuum birefringence directly, it will be the first time a laboratory has used light alone to make the quantum structure of empty space visible. The vacuum would go from a theoretical construct to something you can photograph in a sense, by watching how extreme light bends inside it. And this race to stress the vacuum from the outside connects to something even stranger discovered at the other end of the energy scale. A prediction so extreme, it concerns what observers feel when they move through empty space. A prediction confirmed only by mathematics. A prediction that, if experimentally verified, would change how we understand what empty space is to any given observer. Two observers, same patch of empty space, one sitting still, one accelerating. The still observer measures the vacuum, empty, cold, no particles, nothing. The accelerating observer measures the same patch, warm, full of particles, a thermal bath of radiation washing over them from every direction. Same space, same vacuum. Two different realities, both correct. This is the Unruh effect, derived by physicist William Unruh in 1976, and it is one of the most unsettling predictions in all of modern physics. Here is the physics behind it. When a detector sits still in the vacuum, it samples the quantum fluctuations of all the field modes around it evenly. The fluctuations average out. No net signal, no particles detected. The vacuum appears empty. When a detector accelerates, something changes in how it samples those modes. Acceleration mixes quantum field modes together in a way that does not happen for a stationary observer. Modes that appear as pure vacuum fluctuations to the still observer appear as real, thermal particles to the accelerating one. The two observers are slicing up the quantum field in different ways, and those different slices give different answers about what is present. Unruh derived the exact relationship between acceleration and the temperature the accelerating observer feels. To experience a temperature of 1 degree above absolute zero, an observer would need to accelerate at approximately 247 million trillion meters per second squared. That is roughly 25 million billion times the gravitational acceleration at Earth's surface. For any acceleration achievable with current technology, the Unruh temperature is so small it is completely undetectable. The Unruh effect has never been directly measured. It is classified as a confirmed theoretical prediction. The mathematics are unambiguous. The derivation is accepted by the physics community, but no experiment has reached the required acceleration. This is an unknown waiting for the technology to catch up. What makes the Unruh effect philosophically profound is what it says about the nature of particles. Particles are real. You can detect them. You can count them. But the Unruh effect shows that the number of particles you count depends on how you are moving. The vacuum is observer dependent. There is no universal answer to the question of how many particles exist in a region of space. The answer depends on the observer's state of motion. This is a radical departure from any classical view of space. In classical physics, the contents of a region of space are what they are, independent of who is looking. The Unruh effect says that at the quantum level, that independence breaks down. The same principle applied to the extreme gravity near a black hole's surface produces something even more dramatic. An observer hovering just outside a black hole's event horizon is effectively accelerating due to the immense gravity. By the Unruh logic, that observer should detect a thermal bath of particles emanating from the black hole's surface. This prediction, built on the same foundation as the Unruh effect but applied to gravity instead of acceleration, comes from a physicist who derived it a year before Unruh published his result, and it changes what we think happens to the most extreme objects in the universe. In 1974, Stephen Hawking published a calculation that stunned the physics community. Black holes, he showed, are not fully black. They radiate, slowly, silently. Over immense timescales, a black hole emits a faint thermal glow of particles from just outside its event horizon. Given enough time, even a black hole evaporates completely. The mechanism behind this prediction comes directly from the quantum vacuum. Near the event horizon of a black hole, the immense gravitational field creates an extreme version of the conditions that produce the Unruh effect. Virtual particle-antiparticle pairs form from the vacuum constantly, just as they do everywhere in space. Far from any black hole, both partners annihilate and return to the vacuum within the allowed time. Near the event horizon, something different can happen. One partner falls across the horizon and into the black hole. The other partner, left outside, cannot find its partner to annihilate with. It becomes real. The energy for this real particle comes from the gravitational field of the black hole. The black hole pays a tiny energy debt each time a pair gets split at its horizon, losing a small amount of mass each time. Multiply this over cosmic timescales, and a black hole slowly evaporates, particle by particle, drained by the relentless activity of the quantum vacuum at its edge. The temperature of the radiation a black hole emits, called the Hawking temperature, depends on the black hole's mass. A stellar mass black hole, several times the mass of our Sun, emits Hawking radiation at a temperature so far below any known background that detecting it directly is impossible with current technology. A tiny black hole, far smaller than any known to exist naturally, would be hot enough to detect, but no such object has been observed. Hawking radiation remains an unconfirmed prediction. It has not been directly measured from an astrophysical black hole. However, laboratory analogues have been created. In 2019, a team at the Technion Institute in Israel used flowing sound waves in a controlled medium to create an acoustic black hole, a region where sound cannot escape just as light cannot escape a real black hole. They measured acoustic Hawking radiation from their analog system, confirming the basic mechanism. The connection to the Unruh effect is mathematical and deep. Both arise from the same underlying fact: the quantum vacuum is not the same thing for all observers. Unruh showed that acceleration changes what an observer sees in a vacuum. Hawking showed that the extreme version of that principle, applied at the edge of a gravitational singularity, causes real particles to leak out and drain the black hole of energy. The same physics that makes your vacuum a seething field of virtual particles, the same uncertainty principle that prevents true emptiness, is the physics that makes black holes eventually disappear. Every star that collapses into a black hole carries its fate in the structure of the quantum vacuum. Every particle that ever crosses an event horizon contributes to the slow drain of Hawking evaporation. And every one of those effects traces back to the same fact: the lowest energy state of the universe is alive and it never fully switches off. What physicists learned next was that this alive vacuum is not just a passive force to account for, it can be grabbed, tuned, and used. In May 2025, a collaboration of physicists from ETH Zurich, Princeton University, and the Flatiron Institute published a result in the journal Nature that crossed a line physicists had long debated. They changed the fundamental quantum behavior of a material without touching it, without applying any current, and without using any magnetic or electric field. They used the quantum vacuum. The material was a two-dimensional electron gas, a thin layer of electrons confined inside a sandwich of specially grown crystal called a gallium arsenide quantum well. At very low temperatures, electrons in such a structure form exotic quantum phases that are sensitive to tiny changes in energy. These phases are some of the most fragile and precisely defined states in all of condensed matter physics. Above the material, the team mounted a small piece of gold etched into a ring shape with a gap in it. This is called a split-ring resonator. It is a device designed to support specific electromagnetic modes, a cavity that holds the fluctuations of the electromagnetic vacuum in a concentrated, controlled form. By sliding the resonator closer to or farther from the electron layer, the team could adjust how strongly the electrons were coupled to the vacuum electromagnetic field inside the cavity. No current flowed, no voltage was applied, no magnetic field was switched on. The only thing that changed was the geometry of empty space between the gold ring and the electrons. The results were striking. As the resonator moved closer, the vacuum coupling strengthened. The quantum phase of the electron system changed. Specifically, the team observed a significant reduction in a property called exchange splitting at odd integer filling factors, which determines how certain quantum Hall states form and break apart. The fractional quantum Hall gaps in energy associated with exotic electron behavior that physicists study as potential platforms for quantum computing, also changed. The mechanism was identified as virtual cavity photons, the vacuum fluctuations of the electromagnetic field inside the resonator's cavity, mediating a long-range attractive interaction between electrons. The vacuum was connecting electrons that would not otherwise strongly interact, forcing them into different collective arrangements, restructuring the quantum phase of the entire material. A team at Rice University extended this approach in 2025 using a chiral optical cavity, a resonator designed to enhance vacuum fluctuations of a specific handedness of light. By choosing which type of vacuum fluctuation to enhance, the team could selectively alter the material's behavior in ways that normally require a powerful external magnetic field. Theory predicted this cavity could transform graphene into a special insulating state useful for quantum computing. Researchers at Shanghai Jiao Tong University recognized that these experiments represented the birth of a new field. They gave it a name: vacuumtronics, the use of vacuum quantum fluctuations enhanced through engineered structures as an active tool for controlling the behavior of matter. The vacuum was no longer just a background, it had become a knob, a programmable input, a resource. But the vacuum has been doing this kind of engineering work in nature for a very long time, without any laboratory, without any gold resonator, just physics running automatically at every scale from the atom to the cosmos. The Rice University experiment in 2025 started from a question that sounded almost provocative. Can you replace a magnet with nothing? In condensed matter physics, magnetic fields are workhorses. Physicists apply them to materials to break symmetry, to force electrons into specific quantum states, to create topological phases that otherwise refuse to form. Magnetic fields are effective, precise, and well understood. They are also large, power-hungry, and difficult to integrate into miniature devices. The Rice team, working in a laboratory focused on quantum optics and materials, asked whether the vacuum itself could substitute. A chiral cavity is an optical resonator designed to support only a specific handedness of electromagnetic radiation. All light has a polarization, a direction in which its electric field oscillates. Circular polarization comes in two mirror image forms, left-handed and right-handed. In an ordinary cavity, both forms are equally present in the vacuum fluctuations. In a chiral cavity, the geometry is engineered so that vacuum fluctuations of one-handedness dominate. This handedness is what makes the physics magnetic-like. When an electron interacts with a circularly polarized vacuum field, the interaction breaks the same time reversal symmetry that a magnetic field breaks. From the electron's point of view, sitting inside a chiral cavity where only one-handedness of vacuum fluctuation exists, the experience is mathematically equivalent to sitting in an applied magnetic field. Theory predicted that graphene placed inside such a chiral cavity would develop a topological insulating state, a quantum phase where the material's bulk does not conduct electricity, but its edges carry current with no resistance. This edge current, called a quantum anomalous Hall state, normally requires a strong external magnetic field or extreme cooling to produce. The chiral cavity prediction said the vacuum alone could produce it. The experimental confirmation of this specific effect in graphene was still in progress at the time of the 2025 reports, but the theoretical prediction was detailed and the intermediate experimental results were consistent with the framework. If confirmed fully, the implications extend well beyond graphene. Quantum computing requires specific material phases to build reliable, error-protected qubits. Many of the most promising approaches, including topological qubits based on exotic quantum states, require either intense magnetic fields, extreme temperatures, or both. A chiral cavity that reproduces the magnetic field effect using only vacuum fluctuations would eliminate the magnetic field requirement. Chips that currently need to sit next to large superconducting magnets might instead sit inside precision-engineered cavities, much smaller, much less power-intensive. The vacuum would be doing the work the magnet used to do. Vacuumtronics, at this level, becomes an engineering discipline with direct relevance to quantum computing hardware. The same fluctuations that Casimir calculated in 1948, that Lamoureux measured in 1997, that Ethert Zurich demonstrated altering material phases in 2025, could within years become a design specification in the next generation of quantum processors. Empty space, properly shaped, could be one of the most useful tools in 21st century technology. And that same empty space has been a useful tool in nature for billions of years, long before physicists named it, long before a single laboratory existed. In living organisms, on vertical walls, in the sticky feet of the most agile climbers on Earth, a gecko weighing roughly 2 ounces can hold itself against a vertical glass wall and walk up it with no problem. No glue, no suction cups, no hooks. The surface between a gecko's foot and the glass is dry and smooth. By every classical measure, there is nothing holding the gecko to the wall. The gecko is held there by the quantum vacuum. On the underside of each gecko toe, there are millions of tiny hair-like structures called setae. Each seta splits at its tip into hundreds of even smaller structures called spatulae. At their finest tips, the spatulae are so small that they approach the glass surface at separations where quantum vacuum fluctuations become the dominant force between neutral surfaces. At those separations, a force called the van der Waals force takes over. This is the same family of forces responsible for the Casimir effect. It arises from vacuum fluctuations of the electromagnetic field, inducing momentary temporary dipoles in otherwise neutral molecules. As two surfaces come very close together, the vacuum fluctuations in the gap between them create brief, synchronized electric asymmetries in the molecules on each surface. Those asymmetries attract each other. The attraction is tiny per molecule. Multiply it across millions of spatulae, each making close contact with the glass, and the total force holds a 2-ounce animal to a vertical surface effortlessly. Geckos are not alone. The van der Waals force is responsible for the adhesion of many insects, spiders, and small lizards to smooth surfaces. It is also the reason ordinary tape sticks, the reason graphene layers hold together before you peel them apart, the reason proteins fold and bind to each other in biological systems. Every cell membrane in your body, every protein-protein interaction in every living thing on Earth, involves van der Waals forces. At some level, the quantum vacuum is operating inside every organism, at every moment, contributing to the physical cohesion of biological structures. This connection extends even further. The same mathematical framework that describes van der Waals forces at the molecular scale, the Lifshitz theory developed in 1956 to generalize the Casimir effect to real materials, also describes the forces between colloidal particles in liquids, the forces that determine whether clay settles out of water or stays suspended, the forces that govern how drug molecules interact with cell surfaces. The quantum vacuum reaches everywhere that matter touches matter, everywhere that surfaces come within close range of each other, everywhere that electromagnetic fields can bridge the gap between molecules. It is the underlying mechanism of contact itself at the molecular scale. A gecko on a glass wall is walking on quantum physics. Its feet are measuring instruments, sampling the vacuum fluctuations of the electromagnetic field at the finest scale where animal biology can operate. The same forces that hold a gecko to a wall also appear, in a different form, in one of the most important unsolved problems in physics, a force that operates at the largest scales in the universe rather than the smallest, a force whose origin is the quantum vacuum and whose value, according to every calculation, should be catastrophically larger than what astronomers measure. That discrepancy is the most embarrassing number in all of science. An atom sits in excited state, no light shines on it, no field nudges it, nothing touches it. By classical physics, it should stay excited forever. Energy is conserved. There is nothing to trigger a transition. The atom should remain where it is. After a fraction of a second, it emits a photon and drops to a lower energy state. Where did the trigger come from? This question puzzled physicists for decades in the early 20th century. Classical theory could describe how atoms absorb light. It struggled to explain why they spontaneously released it when apparently left alone. The classical model required some external disturbance to initiate emission. Finding none, the theory failed. Quantum electrodynamics solved it. The atom was never alone. The quantum vacuum surrounds every atom continuously. The vacuum's electromagnetic fluctuations constantly perturb the excited electron, nudging it, jostling it out of its higher energy state. Even in the absence of any real photons, the vacuum fluctuations act as a continuous low-level disturbance. The excited atom interacting with those fluctuations eventually gets the nudge it needs to drop down and emit a real photon. Spontaneous emission is vacuum-driven emission. The quantum vacuum pulls photons out of atoms. This has enormous practical consequences. The light from every flame, every star, every light bulb, every LED screen, every bioluminescent organism in the ocean is ultimately a product of spontaneous emission. Every atom that releases a photon by falling from a higher energy level to a lower one is responding to a push from the quantum vacuum. Every photon ever emitted has the vacuum as a co-author. Laser physics depends on understanding this deeply. Lasers work by stimulated emission, where an incoming photon triggers an excited atom to release a second identical photon. But spontaneous emission is the background process that lasers must compete against and control. Cavities in laser systems are designed to suppress spontaneous emission in unwanted directions and enhance it in the desired direction. This is called the Purcell effect, and it is an early form of vacuum engineering, shaping the cavity geometry to redirect how the vacuum interacts with atoms. The Purcell effect has been used to make more efficient LEDs, better lasers, and more reliable single-photon sources for quantum cryptography systems. Changing the geometry of the empty space around an atom changes how often it emits and in which direction. The vacuum is not just triggering emission, it is the medium through which emission is channeled, controlled, and directed. Every photon in the universe has this history, born from a transition between atomic states, triggered by the vacuum's fluctuations, shaped by the geometry of whatever cavity or medium surrounded the emitting atom at the moment of release. Light itself, the thing that makes the universe visible, emerges continuously from the interaction between matter and the restless ground state of the electromagnetic field. The universe is lit by the vacuum, and at the largest scale of all, the vacuum does something that lights more than atoms. It may be lighting the entire universe, driving its expansion, filling every cubic inch of space with an energy that pushes the cosmos apart. That energy is measured, it is confirmed, and its value compared to what theory predicts is so wrong it has become a defining crisis of modern physics. In 1998, two independent teams of astronomers were studying distant supernovae, exploding stars bright enough to be seen from billions of light years away. They were trying to measure how fast the universe was expanding. Everyone expected the expansion to be slowing down. Gravity pulls matter together. Over cosmic time, the expansion from the Big Bang should decelerate as gravity does its work. Both teams found the opposite. The universe is not decelerating. The expansion is speeding up. Something is pushing everything apart, and the push is getting stronger over time as space itself expands, and this force grows with it. The teams shared the Nobel Prize in Physics in 2011 for discovering what became known as dark energy. Dark energy is the dominant component of the universe. Roughly 72% of all the energy in the cosmos today is dark energy. Ordinary matter, every star, planet, gas cloud, and galaxy, accounts for less than 5%. Dark matter, the invisible mass that holds galaxies together, contributes about 23%. Dark energy dwarfs everything. The most natural explanation for dark energy is the quantum vacuum. Einstein's equations of general relativity allow for a term called the cosmological constant, a uniform energy density that fills all of space. Einstein originally added it to his equations to produce a static universe, then removed it when Hubble discovered the expansion. The supernovae results of 1998 brought it back. A cosmological constant with a small positive value fits the data precisely. And the quantum vacuum, which fills all of space with uniform energy from its ground state fluctuations, is exactly the kind of source that would produce a cosmological constant. The connection between dark energy and vacuum energy is confirmed at the level of theoretical consistency. Both are uniform, fill all space, and produce an effective repulsive force that drives expansion. Dark energy and vacuum energy point to each other. The only problem is the number. Quantum field theory calculates the energy density of the vacuum. The answer it gives, based on summing up the zero-point energies of all quantum fields, is enormous. Astronomers measured the energy density of dark energy. The answer they get is tiny. The gap between the two numbers is at least 60 orders of magnitude, 60 decimal places. Some estimates put it at 120 orders of magnitude. There is no known physical process that explains why the vacuum energy is so much smaller than field theory predicts. The cosmological constant sits where it is, observed and confirmed, with absolutely no theoretical explanation for why it has that value rather than the catastrophically larger value QCD and quantum electrodynamics predict. Two numbers, same physical quantity, a gap between them larger than any other discrepancy in the history of science, and no agreed upon way to close it. This is the cosmological constant problem, and it sits at the center of everything physicists know about the quantum vacuum, because the vacuum connects the smallest physics to the largest structure of reality. Understanding why dark energy has the value it has may require physics that does not yet exist. Physicists are good at numbers. They calculate properties of particles to 12 or 15 decimal places and match experiments with extraordinary accuracy. The standard model of particle physics is the most precisely tested theory in history. Quantum electrodynamics predicts the magnetic moment of the electron to better than 1 part in a trillion. Science has never been more numerically precise. And then there is the cosmological constant. Quantum field theory asks every quantum field to contribute its zero-point energy to the vacuum energy of the universe. Each field fluctuates. Each fluctuation carries energy. Sum them all up. The answer you get, in the most straightforward calculation, is a number so large that if it were real, space would expand so violently in the first fraction of a second after the Big Bang that no particle could ever get close enough to another to form hydrogen, let alone stars, galaxies, or the atoms in your body. the universe would be an infinitely diluted void of individual particles, flying apart forever, with nothing complex ever forming. We exist, therefore the vacuum energy is not that large. Observation pins the actual value to a number roughly 60 to 120 orders of magnitude, smaller than the field theory calculation. 120 orders of magnitude means the theoretical prediction has 120 more zeros than the measured value. No other prediction in science is this wrong by this margin. Physicists describe it as the worst theoretical prediction in the history of physics. Something is cancelling almost all of the vacuum energy. The fields contribute their enormous zero-point energies and then almost perfectly cancel each other out, leaving behind only a tiny residue. But the cancellation is not perfect. A tiny amount survives, and that surviving amount drives the universe's accelerating expansion. The question is, what produces the cancellation? Several proposals exist. Supersymmetry, a theoretical framework that pairs every particle with a supersymmetric partner, predicts that the zero-point energy contributions of particles and their partners cancel exactly. If supersymmetry is perfect, the vacuum energy is zero, but we observe a non-zero value, and experiments at the Large Hadron Collider have not found the supersymmetric particles the theory requires. If supersymmetry exists, it must be broken in a way that explains why the residual value is so small. No complete mechanism for this has been found. A second proposal involves the landscape of string theory. String theory allows an enormous number of possible vacuum states, each with a different vacuum energy. Some of those states have vacuum energies compatible with a universe where structures form. Most do not. The anthropic argument says that observers can only exist in universes where the vacuum energy is small enough to allow structure. We find ourselves in one of those universes simply because those are the only universes where anyone can ask the question. This argument is controversial. It makes no specific testable predictions. Many physicists find it unsatisfying as an explanation. Others consider it the most honest answer currently available. The cosmological constant problem is not a minor loose end. It is a signal that something fundamental about the quantum vacuum is not yet understood. The same vacuum that Casimir calculated, that Lamoureux measured, that Ethak Zurich used to tune a material, has an energy that theory cannot explain at the cosmic scale. And theory has other mysteries too. Several predictions about the vacuum have been confirmed. Several have not. Some may be beyond any near-future technology to test. String theory began as an attempt to unify all the forces of nature into a single framework. Instead of treating particles as point-like objects, it describes them as tiny vibrating strings whose different vibration modes produce the different particles we observe. The theory requires extra dimensions of space beyond the three we experience. Those extra dimensions can be folded and curled in enormous numbers of different ways, and each different folding produces a universe with different physical laws, different particle masses, and a different value of the cosmological constant. The number of possible configurations is staggering. Current estimates put it at 10 to the power of 500. Written out, that number has 500 zeros after the 1. Each configuration is a different possible vacuum state, a different ground state of the quantum fields, a different version of empty space. Each produces a different universe. This collection of possible vacua is called the string theory landscape. In most of those vacua, the vacuum energy is enormous. Space expands catastrophically. No matter forms. In a tiny fraction, the vacuum energy is small and negative. Space collapses immediately. In an even tinier fraction, the vacuum energy is small and positive like ours. The anthropic argument, championed by physicists including Leonard Susskind and Steven Weinberg, says this: only in the universes with small positive vacuum energy can observers form. In all others, either the universe explodes apart too fast for matter to clump together, or it collapses before anything complex develops. Observers like us inevitably find themselves in one of the rare vacuum states compatible with structure, because those are the only states where observers exist to ask the question. Weinberg made a specific prediction from this logic in 1987, before the accelerating expansion was discovered. He argued that the vacuum energy could not be much larger than the amount needed to allow galaxies to form, because larger values would have prevented galaxy formation, and there would be no observers. His predicted upper limit was within an order of magnitude of the value measured in 1998. That match was either a triumph of the anthropic framework or a coincidence, depending on who you ask. The framework remains deeply controversial. Critics argue it is not a scientific explanation because it makes no unique falsifiable prediction. It explains why our vacuum energy is small by saying we could not observe a universe where it was large, but it does not predict exactly what the value should be. It cannot be tested by any experiment. Supporters argue it is the most honest confrontation with the data available. No other framework comes close to explaining why the vacuum energy is what it is. If the landscape is real, the question of why our universe has this particular vacuum state has no deeper answer than the fact that this is one of the states where the question can be asked. Whether the landscape is science or philosophy remains a live debate. What is certain is that the value of the vacuum energy, the cosmological constant, the number that drives the universe's expansion, sits at the heart of every open question about the quantum vacuum. And the vacuum has handed physics several other open questions that may be even harder to close. For all its confirmed predictions, for all the Casimir forces measured, and Lamb shifts calculated, and material phases tuned, the quantum vacuum remains the source of physics' most profound unsolved problems. Each confirmed discovery has uncovered a deeper unknown directly beneath it. The cosmological constant problem stands first and largest. Theory predicts a vacuum energy density at least 60 orders of magnitude larger than what astronomers measure. No mechanism explains the cancellation. Supersymmetry, string theory, and several other frameworks have been proposed. None has been confirmed. The number remains unexplained. The true nature of virtual particles is contested among physicists themselves. The popular description of virtual particles as objects that pop in and out of existence is a simplification that many researchers consider actively misleading. Quantum field theory describes the vacuum through mathematical terms in perturbation expansions. The particle language is a useful shorthand for those terms. Whether it describes something physically real, whether virtual particles truly exist as objects even briefly, is a question that does not have a settled answer. The effects are confirmed. The ontology is not. Whether the 2026 star result fully proves that matter emerged from nothing is disputed. A more precise description says that the collision excited pre-existing quantum fields above their threshold, producing real particles. The fields were always there. The energy of the collision promoted their fluctuations into observable matter. The result is genuinely historic. The framing of matter from nothing requires careful qualification. The Schwinger effect in free space has never been observed. Graphene analogues confirm the mechanism. Oxford simulations predict the signatures of related effects. But a direct observation of electron-positron pair production from a vacuum field, with no material intermediary, remains beyond any current or near-future technology. The Unruh effect has never been directly measured. The temperature predicted for achievable accelerations is so far below any detection threshold that experimental confirmation may be decades away. The physics is accepted by the community. The measurement is not yet in. The proton spin crisis remains open. After decades of experiments, the precise contributions of quark orbital motion, gluon spin, and vacuum effects to the total proton spin have not been fully mapped. The electron-ion collider, currently under construction at Brookhaven, is designed specifically to resolve this, but the answer is not yet in hand. Whether vacuum fluctuations in engineered cavities can induce room temperature superconductivity is a target of active theoretical and experimental research. Several groups have published predictions that specific cavity geometries could sustain superconducting electron pairing through vacuum-mediated interactions. Experimental confirmation is limited. The picture these open questions paint is consistent. Every confirmed fact about the quantum vacuum points toward a deeper layer of physics that remains just out of reach. The boundary between what is known and what is unknown runs directly through the most fundamental property of the universe, the state of its lowest energy. The vacuum is confirmed to be real, active, and powerful. Its deepest nature is still hidden. And that combination, enough confirmed reality to take seriously, enough mystery to keep searching, is what makes the quantum vacuum one of the most productive frontiers in all of science today. What comes next is the largest question of all. Stand at the end of this story and look back at how far it runs. The quantum vacuum gives protons their mass. It built 99% of every solid object you have ever touched. It shifts atomic energy levels with a precision measured to 1 part in 10 million. It pulls metal plates together across empty space. It reaches inside quantum circuits and changes how they behave. It triggers every photon ever emitted from every atom in every star. It holds geckos to glass walls. It drives the expansion of the entire universe. And in February 2026, it handed scientists their first direct glimpse of real matter being born from its depths. This is not a collection of interesting footnotes in physics. It is a single connected story about what the universe is made of at the most fundamental level. The vacuum is the ground floor of reality. Every particle that exists is an excitation above that floor. Every force that acts between particles is mediated by fields whose vacuum state defines how they behave. The Higgs field, the electromagnetic field, the strong force field, the weak force field, all of them sit in a vacuum state, and all of them fluctuate. Take away the vacuum activity, and the physics we know collapses. Atoms do not hold together. Protons dissolve. Mass disappears. The vacuum is not a stage that matter performs on. The vacuum is matter's source material. What does this mean going forward? In technology, the emerging field of vacuumtronics is in its earliest stages. The 2025 experiments demonstrated that vacuum coupling can alter quantum phases in two-dimensional materials. Theory predicts that engineered cavities can substitute for magnetic fields in quantum computing devices. As fabrication technology improves, and as researchers learn to sculpt the geometry of empty space with greater precision, vacuum engineering will become a tool in semiconductor design, quantum computing hardware, and possibly in developing materials with properties that conventional approaches cannot achieve. Room temperature superconductivity, one of the most sought goals in material science, has been predicted in some theoretical models to be achievable through vacuum-mediated electron pairing in specifically designed cavities. The experimental confirmation has not arrived, but the framework for pursuing it now exists. In fundamental physics, the quantum vacuum connects the two great theories that have so far refused to unify: quantum mechanics and general relativity. Hawking radiation emerges from applying quantum field theory to curved space-time near a black hole. The cosmological constant connects vacuum energy to the large-scale structure of the cosmos. Any complete theory of quantum gravity must explain the vacuum energy, must resolve the cosmological constant problem, and must account for the observer dependence revealed by the Unruh effect. The vacuum is where the two great unfinished projects of physics meet. In our understanding of reality itself, the quantum vacuum forces a rethinking of what existence means at the most basic level. The boundary between something and nothing is not where it appeared. The boundary between virtual and real is not fixed. The boundary between observer and observed is not absolute. These are not philosophical abstractions. They are conclusions forced by measurements made in laboratories with real equipment producing real data. The universe at its deepest level is a field that never rests. You are inside it now. You are made from it. Everything you can touch or see or measure emerged from its fluctuations long ago, and those fluctuations continue to shape every particle in your body at this exact moment. Empty space was always the most important thing in the universe. It took physics most of a century to find out,